All right, you guys, I'm going to start on this rock section, and we're going to start with the rock cycle. Now, I've made a little video of the rock cycle, and you guys really need to look at that. It's kind of surprising that that's something that kind of messes students up. All right, so the definition of a rock, remember you had to know the five-part definition of a mineral, but the definition of a rock is a lot easier. I usually remember it in two words. A rock is a mineral aggregate. Now if that doesn't mean anything to you, just say rocks are made up of minerals. So you might say, well, why did we learn minerals? Because minerals are the building blocks of rocks. There are three different types of rocks, and they've been separated out according to their mode of origin or how they were created. Okay, we're also going to talk about the rock cycle. Now, the three different types of rocks, igneous rocks. Okay, most of you guys have seen igneous rocks. You might have been on an old lava flow, or maybe you have a granite countertop. Those are the type of rocks that are formed from liquid rock. And molten rock below the Earth's surface, we're going to find out, is called magma, and that's what will create your granite countertop. And liquid rock that flows at the Earth's surface is called lava, and that might create, basalt like the entire big island of Hawaii. All right, sedimentary rocks. Sedimentary rocks are made up of pieces of pre-existing rock. And these sediments are compacted and lithified, changed into rock. All right, and then the last type are metamorphic. Metamorphic rocks are rocks that have been changed. And typically the agents of change are temperature and pressure. All right, be sure to look at that video I put together about the rock cycle. You have an in-class assignment, it will be on the exam. Now, the rock cycle is kind of interesting because igneous and metamorphic rocks are mainly made from the internal heat of the Earth, which is that radioactive decay that happens in the core. But sedimentary rocks are basically created by the external heat source or powered by solar radiation, the energy of the sun. Now, geologic processes, that sounds kind of scary. Remember, melt is a geologic process, so it's really not that bad. Watch that video. And what's important about the rock cycle is, yeah, an igneous rock can become a sedimentary rock. An igneous rock can become a metamorphic rock. I mean, it's how we change rocks from one type to another. It happens all over the Earth. And it's also the way that we transfer material from the atmosphere, the ocean, the land, inside, outside the Earth, etc. So it's pretty important. All right, the video has a sample of something probably similar to this. I think it's actually out of order from this. But remember, I can put this in any order. All you care about is if the arrow is pointing at igneous rock, you have to melt whatever the pre-existing rock is. If the arrow is pointing at metamorphic rock, you subject it to heat and pressure and it changes. Now, yeah, the steps for the sedimentary rocks are much more lengthy. And when we get to sedimentary rocks, believe me, we'll go over those. But any type of rock, you need to uplift it to the Earth's surface, okay, expose it to the atmosphere and water, and it's going to be weathered, and weather just means chemical and physical breakdown, so we're making sediments. Okay, you're going to take those chemical and physically broken down pieces of rock and transport them. Okay, they get transported like in a river until they get deposited. They get deposited, and usually more stuff gets deposited on top, buried then and compacted, and finally the last step, lithification, lithos, rock, the act of making a rock. So again, watch that video. I put a little bit of time and effort in there, so it's there for you. All right, so this is, again, to make an igneous rock, you must melt a pre-existing rock. To make a metamorphic rock, you subject it to heat pressure, and it changes. There is a third agent, and it's chemically active fluid. You guys, that's just hot water. And then the last type, there's a few more steps, and you do need to know most of those steps. You've got to know uplift, weather, transport, deposit, and lithify, okay? Because you can't just put one or two words on there. All right, the other thing is that just kind of, if you looked at your example that you have of the rock cycle, you see a lot of lines or arrows going through the middle, and that just shows you that if I want to make an igneous rock into an igneous rock, I just melt it again, okay, and that does happen. So it doesn't have to go from A to B to C, but you need to know the processes to take a rock from one type to another. All right, we are ready to start on igneous rocks. Now, I guess I am a sedimentologist, and my specialty is sedimentary rocks. But if I could go back in time, I think I would become a volcanologist, and I would study igneous rocks. They are absolutely fascinating. Now, all igneous rocks actually start off as magma or liquid rock beneath the Earth's surface. Now, not all magma makes it to the Earth's surface to form lava. Lava is liquid rock at or near the Earth's surface. Now, if magma cools beneath the Earth's surface, it's going to cool more slowly. If you guys think about miners, let's say it's snowing at the surface in December in Pennsylvania. Okay, and those miners, they're in their Arctic survival wear, and they get into the mine and they start going down, thousands of feet maybe. Believe me, it's like a strip tease. They start pulling off their clothes because the deeper in the earth you get, it starts to get hotter and hotter and hotter. And this type of rock is forming 5 to 7 miles beneath the Earth's surface, deeper than any miner. And so when it's cooling in a pretty hot environment, and so it's cooling rather slowly. When it cools slowly, those minerals are able to form larger crystals. So think about your granite countertop. Okay, your granite countertop is beautiful because it's got big, mosaic of crystals, and those formed slowly beneath the Earth's surface. Okay, rocks that form inside the Earth, igneous rocks, are called plutonic. Okay, pluton, we're going to talk about plutons, or intrusive because they're inside the Earth. All right, some of that magma will make it out to the Earth's surface. Everybody has seen a video or maybe even a live eruption of a volcano. When it makes it to the Earth's surface, we call that lava. Now, lavas range in temperature from like 1200 degrees Celsius to about, 700 degrees Celsius. And a hot day on Earth, the hottest day on Earth, might be 37 degrees Celsius. Okay, that's like Death Valley in the summer. Okay, think about it, 1200 degrees Celsius, 37 degrees Celsius. When this lava comes out to the Earth's surface, it's going to cool really, really quickly. It's cold at the Earth's surface for this lava. And because of that, the crystals that form are going to be really, really small. They might be microscopic, probably microscopic. Okay, we call rocks that form from lava at or near the Earth's surface volcanic or extrusive because they extrude out onto the Earth's surface. All right, we are eventually going to classify our igneous rocks, and it's actually pretty straightforward. If you guys are in the lab, you'll really get this. When we look at rocks, first of all, it's really easy to tell the 3 different types of rocks once you've had some experience with them, just by looking at their texture, the way they look or feel, and the way the minerals are aligned or laid out. It actually gets to be pretty easy. And then the other thing that we use are what minerals are in that rock. Okay, so we're going to start with something called texture, or the size and arrangement of crystals. Kind of already given you a hint. Kind of 2 main textures are going to be coarse or large crystal and fine or small crystal. And we already talked about how you get big crystals or coarse grain crystals when you cool slowly beneath the Earth's surface, and fine grain or small crystals when you cool fairly rapidly at or near the Earth's surface. So we're already on our way. All right, crystallization. We talked about this again, the act of cooling, making that regular repeating internal structure in our solid. And what determines how big the individual crystals are is how fast it cools. The slower it cools, the more time we have to make those individual crystals, and then the minerals are pretty large. Okay, so slow rate makes large minerals, a fast rate makes really tiny minerals, and sometimes it cools so fast that it does something that we call quench. Okay, quenching, and that forms glass, and we'll talk about a volcanic glass. You guys all know obsidian, so we'll talk about that. There is no regular repeating internal structure in obsidian. It quenched. It's chaos in there. All right, we're going to talk about some of the different textures. Now, you guys, I give you both the real scientific name that we geologists use, but I'll always, put 2 words. So, like if I'm talking to another geologist, I say, oh yeah, it's an aphanitic texture, but I'll always have both words there. Aphanitic means fine grain. Okay, A means without. If you're agnostic, you're not have a church. If you're atheist, you don't have a God. And if you're aphanitic, you don't have visible crystals. So fine grain means that you cooled fast. Okay, glassy means that you cooled really, really fast. And in fact, you have no regular repeating internal structure. Vesicular, you guys, Swiss cheese is vesicular. Okay, that's gassy lava. Sometimes lava has bad gas. Okay, and one great example is pumice. I think you guys all know pumice. All right, and then the last of these volcanic textures or extrusive textures that I'm going to talk about is pyroclastic. Pyro, fire, clastic, broken. If you've ever seen a video or a live volcano erupting, anything that's coming out of that volcano, ash, solid material, bombs, etc., those are pyroclastic textures. And they have kind of a specific texture because they are fire broken. It's very violent. All right, here is a picture of a rock that we're going to learn later. It comes in pink, it comes in cream, but if you kind of look at it, you don't really see any visible crystals, okay? And this is aphanitic, or very fine grain. Now, if you got out like a jeweler's loupe or a good microscope, and you really zoomed in on this, it would look like your granite countertop, okay? If your granite countertop, instead of forming slowly beneath the Earth's surface, had erupted out as lava onto the Earth's surface, this is what you would have, okay, very fine grain. All right, here is that glassy obsidian. Everybody knows obsidian. This lava came out and it quenched. It cooled so fast that there are no visible crystals, even under magnification. It's chaos. So this would be a case of that, no regular repeating internal structure, just pure chaos in there. All right, here's another vesicular texture. We talked about pumice. Pumice is the light-colored lava with bad gas. This is the dark-colored lava with bad gas. And you guys can see the holes, and those are kind of fossilized escape channels for the gases. Sometimes lava is gassy, sometimes it's not. We'll talk a little bit about that. All right, here is a picture of the side of a volcano after an eruption. You can see all that material that's been laid down. You can actually see the layering of it as the older stuff's on bottom, younger stuff on top. And then to the right are things that we call volcanic bombs. Okay, and these are lava that has flown through the air, and a lot of it takes like kind of a Nerf football shape. It's called fusiform because as it flows through the air, it's cooling pretty rapidly, and it gets that kind of aerodynamic shape. And yeah, you don't want to be hit by one of these. It would not be pretty. So these are both pyroclastic textures, as is ash. So we'll look at that later. All right. Coarse grain textures or plutonic intrusive textures are going to be larger crystals because this magma cooled more slowly beneath the Earth's surface. Now, granite is phaneritic, okay, but we will always, again, mention it as coarse grain and then maybe in parentheses phaneritic. And because of its slow rate of cooling, it has big crystals. Now, typically, these crystals are between 1 millimeter and 10 millimeters in size. Well, once in a while, if you guys hike in the Sierra, you probably come across these little pockets in those granite and granodiorite outcroppings of really huge crystals. Those parts of that magma cooled even more slowly. They may have taken 1 million, 10 million years, something like that to cool. And when the individual crystals, all of the crystals in your coarse grain rock are bigger than 1 centimeter, okay, that's 10 millimeters, then it's called pegmatitic. Okay, and it's really, really pretty. I love pegmatitic texture. Okay, and sometimes some of those pegmatites, or the large crystals, are valuable. All right, here is a typical granite, and it's got pretty good sized crystals. Once you had the mineral part of your lab, you'd be able to look at that and say, oh yeah, I see smoky quartz, I see muscovite mica, I see potassium feldspar, I see biotite mica. Okay, and I can even see that from this scale. Obviously, it'd be nice to have the hand sample in your hand, which is why lab is so great. But this is considered coarse grain. The individual minerals are all bigger than 1 millimeter. They're visible to the eye. That's what phaneritic means. Now, just to make things a little tougher, once in a while we have rocks that display both textures. You guys, picture a volcano. Okay, when a volcano erupts, it's kind of analogous to you vomiting, okay? Terrible analogy, but, in order for you to actually vomit and have stuff come out, you have to have something in your stomach. Otherwise, it's just dry heaving, right? And so the stomach in a volcano would be the magma chamber, which is below the volcano. Now, some volcanoes only erupt every, 400 years, 1,000 years, 200 years, just depending on the different type of volcano. And so if you have that stuff sitting in your stomach, it would obviously, dissolve away, but in a volcano's case, if there's something, if the magma is sitting down in the magma chamber, it starts to cool and crystals start to form. And the crystals that will form, those minerals, will be the highest temperature minerals. Okay, so they're down there forming, and the rest of the material is molten. Okay, well now the volcano becomes active and blah, it barfs forth. Therefore, what comes up would be those big crystals with that magma now becoming lava, and that lava is going to cool really quickly. So you'll have big crystals in a fine-grained matrix. So they started to cool slowly beneath the Earth's surface. You're going to have big crystals of the highest temperature mineral or minerals, and then it comes up to the Earth's surface. The rest of the material that was still molten cools rapidly with a fine-grained texture. So that's called porphyritic, and it's actually pretty common once you know what you're looking for. All right, here's a porphyritic texture. You can see the big crystals. Those are all white. Notice they're all the same material. They're all the same mineral. And then you can see the gray matrix surrounding that. That's the fine-grained stuff that cooled rapidly. So porphyritic. All right, if you guys go into your PowerPoint, I have recorded an audio lecture specifically about Bowen's reaction series and Dr. Bowen, the geochemist, who kind of discovered this. But what he discovered is that there is a light-colored mineral that does form at a high temperature, which is not the norm. And that is a calcium-rich plagioclase feldspar. The feldspars are the naughty minerals, and so they, you know, kind of break a lot of our rules. And then for some reason, the addition of calcium allows that feldspar structure to form at a much, much higher temperature than you would ever expect. So listen to that audio lecture. Now, this is kind of cool. If you guys are in lab, you'll probably end up going to Griffith Quarry and then an area across on Gilardi Street in Penryn also. And you get a great example of this. Griffith Quarry is a place where they mined or quarried granite diorite, and it's in, you know, Folsom Prison and the base of the San Francisco Mint, and it's a igneous intrusive rock. Okay, and so if you look at that magma body, as that magma body cools, obviously the first thing that forms are mainly those dark minerals, right? The higher temperature minerals. Yeah, calcium plagioclase also forms. But your olivine, your augite are forming, and they are full of iron and magnesium, and so they're more dense. And so basically they fall out to the bottom. Okay, and what that leaves is the rest of the magma poorer in iron and magnesium. Okay, imagine this. You've got a greatly stocked pantry and you love chocolate chip cookies. I go into your pantry and I steal all your chocolate chips, and I take the chocolate bar so you can't make your own. Okay, you can't make chocolate chip cookies anymore because I've taken away the chocolate chips, and in a way you're removing the chocolate chips and you're leaving, you know, something that's much more like a cookie, a sugar cookie batter or something. Okay, now Griffith Quarry would be kind of at the last stuff, the kind of sugar cookie stuff. But off Gilardi Street, there is a site where you can find the dark material, the gabbro, the olivine, the calcium plagioclase feldspar, and the augite. Okay, and so a magma that was originally, you know, if this magma at the top picture had erupted on the Earth's surface, it would have been basalt or black lava. But by the end, it's changed to that if it erupted out, it would have been pink or cream lava or light colored lava. So the magma body can change its chemical composition over time. So kind of exciting thing. All right, we are going to start by naming igneous rocks, and I am going to give you guys a video, a separate video of this with the igneous rock table and actual examples. So we're going to look at texture, and we're going to look at color, or, you know, amount of light colored minerals versus dark colored minerals. Okay, now if you were in our lecture room, in our lab room, we've got walls of igneous rocks, and if, let's say, there was an earthquake and they all fell onto the floor and mixed up, it would be so easy. I'd pull them down, I would separate them light, intermediate, and dark, and then I could also separate them, you know, according to their texture. It would be very, very simple for me to put them back in order, and I think if you guys were in lab, it would probably be pretty simple after you've had your lab for you to put them back into their proper spaces. All right, now important words. Felsic, I don't like felsic, I like silicic. Silicic igneous rocks are rocks that are primarily composed of the light colored minerals, okay, mainly quartz, potassium feldspar, sodium feldspar, muscovite. Yeah, they may have some biotite and maybe even a little hornblende, but my analogy, this would be mainly salt, not a lot of pepper. So imagine I took a whole bunch of light colored salt, poured it out, and just sprinkled a little bit of pepper on it, okay? And so those would be my felsic or silicic rocks. These are lower temperature. All right, now this is the exception to the light versus dark rule. Yeah, a lot of obsidian is black. Why is it black? It is black because of the chaos. It's kind of like the Roach Motel. Roaches check in, but they don't check out. Light goes in, but it doesn't come back out. Now you guys remember, if this same exact lava that quenched had had bad gas instead, it would be pumice. And I take students to a site by Mono Lake where we collect boulders that have fingers of pumice and obsidian together. And so you can actually see they're chemically exactly the same material. It's just that this quenched and therefore it's dark in color. This is mainly quartz, okay? It is not mainly dark minerals. All right, here's if that obsidian flow had instead had bad gas. Here is your vesicular pumice. So remember the Swiss cheesy texture, the holes are escape routes. For the gases, this is very, very low density. In some cases, your pumice can float. All right, here is the pink variety of rhyolite. It is also full of light-colored minerals. Basically, the last three rocks that we've seen, the obsidian, the pumice, and the rhyolite, if I ground 3 separate samples of each of those and sent them off to a lab, they could come back chemically exactly the same. The big difference is their texture. And again, this would be chemically, could be exactly the same as the granite on your countertop if you have a pink granite. It's just this cooled rapidly at the Earth's surface and your granite countertop cooled slowly beneath the Earth's surface. All right, and here is that light or creamy color rhyolite. We're going to talk about rhyolite, you guys. When we talk about volcanoes, these are the most dangerous type of volcanoes, and the good news is we haven't had one erupt in our lifetime, okay? The bad news is if one, Yellowstone is an example of one erupted, it would ruin the United States. So we'll talk about that. It's kind of exciting. Don't lose sleep, you guys. So here's the creamy color. Again, mainly light-colored minerals. The last version of it is pink because it contains a lot of that potassium feldspar. All right, here is, again, felsic or silicic rock, mainly light-colored minerals. Here's your granite, so a little bit more coarse grain. It cooled slowly beneath the Earth's surface. All right, and then here's your pegmatitic granite. You guys, that is a big Swiss Army knife, one of those old-fashioned, like 7-inch long ones. And so there's, in the background, you can see typical Sierra Nevada granodiorite. And right here is a pocket of that very, very, very large crystals. Okay, so pegmatite. All right, intermediate. Intermediate in temperature, intermediate in composition. Now, again, bad analogy, but equal parts salt and pepper. You guys, there is no salt and pepper in these rocks, okay? I'm just using it as an analogy. So equal parts light-colored minerals, equal parts dark-colored minerals. All right, andesite. Andesite is a gray volcanic rock that, if you've been up to Mount St. Helens, you've been to the Andes volcanic mountain chain in South America, that's the main rock that forms those mountain chains, the Cascades and the Andes. Okay. Now, andesitic ash, this is Mount St. Helens ash. There is still a lot of this stuff around. It's gray in color. It's not pink, it's not creamy, it's not black, it's gray, because if you kind of mix the cream and the black, you get gray. So intermediate. All right, this is what it looks like when your coarse-grained igneous rock has equal parts salt and pepper. And this is called diorite, okay? So diorite, equal parts salt and pepper. All right, and then here is a porphyritic andesite. So remember the porphyry, where you have the big crystals in the fine-grained matrix. You can see the gray matrix surrounding this. You have the dark crystal being the highest temperature one, the large crystal here. So that is your porphyritic andesite. So obviously, something like Mount St. Helens could produce this because Mount St. Helens periodically erupts. All right, mafic rocks. In fact, most igneous rocks on the Earth's surface are mafic, or made up of dark colored minerals. So mainly the olivine, the augite, and the calcium plagioclase feldspar, that kind of naughty white mineral that you sometimes find in there. They're called mafic, Ma for magnesium, Fic for iron, because they are iron and magnesium rich. So they're actually darker in color and denser. All right, here is the most common igneous rock on the Earth's surface, and this is basalt. The entire big island of Hawaii is made of basalt. You can also find basalt on top of Table Mountain in Oroville, and also on top of Castle Peaks up Highway 80. So we do have some basalt. The entire ocean floor is lined with basalt, so we're going to talk about that. Okay, so dark in color, fine grain. All right, these are basaltic lava that has flown through the air during a volcanic eruption and taken that funny fusiform shape. Now you guys, these are the same chemical rocks, except the one on bottom has rusted or oxidized. If you contain a lot of iron and magnesium and you're in an environment, maybe it's wet or something that makes it just a little bit different, it can really turn red pretty quickly. So that's just rusting or oxidation of this dark iron-rich rock. All right, here is basalt with bad gas, and we call that scoria, Scoria. Now, I'm from Southern California, where we have some bad droughts, okay? We didn't get rain for 7 years when I was young, and people ripped out their lawns, and actually a lot of them put this material in, you know, as decorative rock or something. So basalt with bad gas, scoria. All right, now this is gabbro. It's a little difficult to see from this picture, but if you look, there's actually large, dark crystals, green crystals of olivine, black crystals, blackish green crystals of augite, and a couple of lighter colored minerals, the calcium plagioclase feldspar. This is the rock that we find just off Gilardi Street. So we have a Penryn example of this, and in fact, if you ever come in my office, ask me to show you my gabbro, because I've got a lot from the Penryn Pluton. All right, now, yeah, there are ultramafic rocks that have been exposed onto the Earth's surface. So what are they? They're mainly made up of olivine. So they are rare at the Earth's surface, except up here we actually have a lot of them. Up Highway 80, kind of near Alta, we actually have what's called the Feather River Peridotite Belt. So typically they're rare at the Earth's surface, but not in Placer County. So the coarse grain version is called peridotite, and I hope I have a picture of it. And it's mainly made up of olivine with a little bit of pyroxene. It's what makes up the next layer down of the Earth. We're on the surface layer, and we'll kind of talk a little bit more about these layers of the Earth in the next section. All right, now if that material were to erupt out at the Earth's surface and cool really rapidly, it made this rock called comatite, and yes, that's how you spell it. Now, luckily, this doesn't form anymore, because what would cause this to form would probably the Earth being torn apart, like a large impact from a space object or something. And so this is all material left over from kind of the initial layering and violent beginning of the Earth, when the Earth was still clearing its orbit. And there's very little of it left, but sometimes you can find some, and it's in a lot of museums. Okay, so here is the peridotite. You guys can see big green olivine crystals and a little bit of the blackish green augite crystals in there. They're big. Okay. And then here's comatite, and the picture's not great. It was taken through plexiglass at a museum, but this is basically probably at least 4 billion years old, and it's what would happen if that magma that was very mafic had erupted out at the Earth's surface and rapidly cooled. It's basically a volcanic glass, so kind of rare. All right, now I will make a separate video about your rock table and your igneous rock ID, but kind of the main six-pack here you can see highlighted. And again, look on the left-hand side, texture on the top axis that we have is mineral composition. On the top part to the left we have felsic or silicic, to the right we have mafic. And then it looks like we're starting with coarse grain, fine grain, mixed porphyritic, and then glassy. Now I don't agree with this 100%. The pumice and the obsidian need to be way on the left-hand side. They are felsic. They do not go andesitic and basaltic, but this is just kind of a table, and you'll see I'll fix the table when I give you a table. But granite, remember its extrusive equivalent is rhyolite. Those are my felsic igneous rocks. Diorite and its extrusive equivalent andesite are my intermediate intermediate composition rocks, and then gabbro and basalt, its extrusive equivalent, are my mafic. And there you can see the peridotite and the comatite. And again, if you make it to a museum, look for comatite.